Greetings and welcome to Particle Physics. My name is Stephen Pollock. I'm a professor of theoretical nuclear and particle physics at the University of Colorado in Boulder. Those words may or may not mean a whole lot to you right now. Theoretical nuclear and particle physics. It's a branch of physics, and by the end of this course you're going to have a very good sense of what those words mean and what it is that I study and that we're going to be learning about in this course. Particle physics. It's a branch of physics. Physics as a whole is just the study of what the world is made of, how things work, how they behave, why they behave that way. It's trying to understand things and phenomena, both natural and technological. In the ordinary world, you toss a ball up in the air and it follows an arc, and we can understand that path. It makes sense. It follows certain laws of physics. Particle physics is a branch of this study where we really try to get down to the bare bones. What is the world made of at the smallest level? What are the simplest building blocks and the most fundamental rules and ideas which govern how things work, why they behave the way they do? Particle physics is about the particles that make up the world that we live in. I could describe particle physics in 5 words. Those 5 words are somewhat technical. They're defined by physicists to have very definite meaning, but they also connect with our everyday intuitions and uses of those words. Force and energy, matter, space and time. Those are the 5 building blocks of the field of particle physics, and in fact, of much of physics itself. Force and energy refer to how and why things interact. Matter, what are the things? What is the world made of? Space and time, what is the framework in which all of that stuff is going on? These are the concepts of particle physics, and as we go on in this course, we will be dealing especially with the middle, the matter, and also with all of the other elements, the forces that matter feels, the energy that is involved in these interactions, the space and time in which they live. Look around you for a moment. Think about the world that you are in right now, the physical world, the objects and the phenomenon. There are hard things wherever you might be that are so hard you could try to break or bend them and you couldn't. There are also soft things like your hands or your skin. There's ethereal stuff like the air that you live in that you can just barely detect or sense. And then there's the things going on in that world, the sound that's hitting your ears and the light that's striking your eyes, the colors, the textures. All of that stuff is the realm of physics. And you could imagine that this enormous diversity of phenomena is overwhelmingly complicated. I mean, you can have this sense of the world as being filled with a whole bunch of different things, and we could study any one of them. That might be a branch of science, and it's hard to imagine that you can tie it all together. But we can. This is one of the wonderful things that we have learned about the world, is that everything physical, from objects in this room, objects in outer space, objects in the deepest galaxies, and everything in between, all arises from a very simple set of rules and a very simple set of ideas and fundamental building blocks. So that's where we're going in this course. What are those ideas? What are those building blocks? How can we make sense of them? Let's go back 2,500 years. This is an old question. People have been puzzling about what the world is made of from time immemorial, and I guess they didn't write it down in the days of cave people, but we do have records of Greek philosophers thinking about this. What is the world made of? We're going to be learning in future lectures about some of these folks and their ideas, but let me summarize sort of 2 viewpoints that arose 2,500 years ago. There was Democritus, a Greek philosopher from about 400 BC, who had this idea. He wasn't the originator of the idea. He was following in a long tradition of other philosophers who were thinking about how the world works. And his idea was that everything is made of little chunks. He called them atomos, which means unbreakable or uncuttable. Let me give you a kind of a concrete metaphor to think about Democritus' idea in real terms. Let me hand you a stick of butter. Okay, this butter is an object, it's a physical object, and it has certain characteristics. it is yellow and it's soft and it melts if you heat it up and it has a certain heft to it. You can describe it, you can study it and understand it. It's a material object. Now what if I chop it in half and throw away half and you're left behind with a half a stick of butter? I think we would all agree there's still butter there. It's less massive, but it's still definitely butter. We haven't changed the essence or character of this material. So if you want to understand butter, it doesn't matter how much I give you. So what if I chop it in half again and again and again? So now you've got a pat of butter. It's still butter. There is no difference between the pat of butter and the original stick except for how much I gave you. And now Democritus is imagining, what if I keep cutting it in half and in half and in half again and again? Ultimately, believes Democritus 2,500 years ago, we will come down to a chunk, an individual, indivisible, uncuttable chunk of butter. It's physical, it's real, it's a little thing that you could imagine seeing or looking at, although it turns out that it's much smaller than anything you could actually see with your eyes. And this is Democritus's idea of atoms. They live in the void. They move around, they interact with one another, they're real, solid, physical objects. Okay, that's an idea. It's a philosopher's idea. And there were other philosophers at that time who disagreed completely. In fact, Aristotle, probably one of the most famous philosophers of that era, disagreed a lot, and in fact, most of what we know about Democritus's ideas come from Aristotle's critiques. Aristotle had an idea which by modern standards is a little more nebulous. He believed the world is made of earth, air, water, and fire, but they're not physical chunks. They're more like characters or qualities. And so matter is infinitely divisible. You can keep cutting that butter into smaller and smaller and smaller bits forever. It's butter all the way. Aristotle's ideas survived for thousands of years. He was a very brilliant man in many respects, had a lot of influence in the fields of religion and religious philosophy and philosophy in general. Many of his scientific ideas, this one in particular, are really quite discredited now. There is no evidence of what Aristotle had to say, and there is a lot of evidence for what Democritus believed. But neither of those fellows was a scientist in any modern sense of that word. They believed that you can understand the world just by thinking about it. Just be a philosopher. Ask yourself, how should the world be for it to make sense? That turns out to be a very unproductive way of understanding how things work. It's much better to go into the laboratory and ask nature, how are things? Not what do we believe is the way it should be, but just take data, collect information, and ask yourself, how does butter behave? And you can discover, it took over 2,000 years, it was in the 1800s that people began to come up with concrete evidence that indeed butter is composed of what we would now call molecules. And then at a later time, we discovered that those molecules themselves are understood to be built up out of even smaller objects, which we now call atoms, after Democritus's original idea. So this puzzle about how the world works has been around for a long time, and it remained unsolved for a long time. And I would argue that it has been solved today. Yeah, I know that sounds a little bit like an arrogant physicist's statement that we understand the world. And I'm going to put lots of asterisks on it, and as the course goes on, we're going to really be talking about what we do know and what we still don't know. What are the remaining puzzles, and what are the deep questions that we have not yet resolved? But to a very large extent, we do know that the world is made of atoms. We have direct physical evidence. We have electron microscopes that can image individual atoms now, and even subatomic particles. The atoms are themselves made of smaller constituents. The true building blocks of nature are smaller than atoms. That's a fairly recent idea, and one which we're going to be visiting over and over again in this course. And even those subatomic particles, we have direct evidence. They leave little trails behind them in particle detectors, kind of like the trail you see when you look at a jet airplane. Even if you can't see the jet, you can see direct evidence of its passing. And in this course, we're going to learn about that data and the ideas that we have built up around the data to try to make sense of it, to try to understand it. Let me give you an analogy so that you can get the sense, as I do, that this idea of atoms and subatomic particles is really well understood. There's another scientific idea that these Greek philosophers debated, which was our place in the universe. A very different question. For instance, do we live on a flat Earth, or is it a ball? Are we the center of the universe, or is something else the center, or is there no center? Okay, these were all legitimate questions for people to be asking and to be curious about. And again, there were different philosophical camps 2,500 years ago, and there were in fact Greek philosophers who believed a contemporary version of the way the world works, but they weren't really collecting data and making measurements, watching the planets move through the night sky, and it really took 2,000 years to the Renaissance and afterwards for people to begin to make definite statements. And today, we all have this worldview. It's taught to us as little children in elementary school that the sun is at the center of the solar system and the planets go around in orbits around it, and we can make sense of a phenomena like, for instance, that the sun rises in the east, travels across the sky and sets in the west, without invoking this kind of primitive idea that we're at rest and the sun is going around us once a day. Okay, I think we can say with conviction that that's not a scientifically valid idea, and I think pretty much everybody will agree with me. If you disagree with me, it's worth thinking about why we know that, and even if you do agree with me, it's worth asking yourself, how do you know? Why is it that you believe this picture that was given to you, handed to you by your elementary school teachers, that it's not the case that the sun is rotating around the earth once a day? There are many good reasons to believe that. There's lots of data. There are many experiments and measurements that you can make. In fact, even ones that you could really make. And it's fun to think about. And it's something we're going to think about throughout this course. When I tell you about scientific facts, these facts are all based on evidence, and you should always be asking yourself, how do I know? Why do I believe that? The goal of this course, then, is to give you the framework. It's much like this framework where I could describe the solar system and you could have a mental model. And once you have a mental model of the solar system, you could understand news reports about satellites in orbit around the Earth or rocket ships heading out towards Saturn to explore it. You have a mental model, a framework into which you can fit contemporary ideas and explorations and discoveries and make sense of them. And what I would like to do is to give you such a mental framework to understand the contemporary ideas that we have about particle physics, about the fundamental building blocks. It's a model which is not so common, although I think lots of people do have some idea, some crude, intuitive sense given to us in our elementary school and through high school training about what an atom is. But we're going to go deeper. We're going to look beyond atoms and ask what they're made of, and what they're made of is made of, and we're going to follow this chain as far as we can. Particle physics' goal is to try to get to the bottom. And this leads me to an idea. It's a kind of a philosophical idea, an approach to understanding the world, which I call reductionism. Actually, everybody calls it reductionism. It's the idea that when you look at something complicated, there are many ways to try to understand it. And one of the ways is to try to ask, what is it made of? What are the kind of more universal building blocks? That's a reductionistic approach because it reduces a complicated thing to a simple thing. Now, this is not the only way to approach science. If you're looking at human beings interacting with one another, and you say, what's going on? How do I understand the conflicts and the discussions, human psychology or sociology? You could, in principle, think about that by investigating human beings and looking at various aspects of their interactions. Or you could be a reductionist and say, let me study the human brain, and let me try to understand human behavior in terms of the chemical and physical makeup of the brain. Now, it's certainly not the only way to understand human behavior, but I would argue it's a useful way. We can come up with drugs, perhaps, if somebody is dysfunctional. In some cases, it really does boil down to a chemical imbalance. In other cases, it requires psychotherapy. Right? There's lots of possible approaches that you could imagine. The reductionist one being only one of many, but a very powerful one. If you ask a doctor, how does the human body work, especially a sort of a Western doctor, I think their approach is to a large extent, reductionistic. They say, well, the human body is a collection of organs, and those organs are fairly universal. People have hearts, and dogs have hearts, and worms have hearts, and so we can understand complicated systems in terms of the fundamental building blocks and how they fit together. You got a heart and lungs and bones and skin, and we need to understand not just what those parts are, but how they hook together. Now, that's not the only approach to medicine, and it may ultimately just be one of many useful approaches, but I think we can argue that it's definitely a useful, valuable scientific approach to do that, to think reductively. And as a physicist, I think we tend to think reductively to deeper and deeper levels. I mean, what's a heart? What is a heart? How does it work? Well, to me, the way a heart works primarily is it's made of a bunch of cells of a certain type, and they have a certain structure, and they interact with one another in well-defined ways. So again, I understand this complicated thing by reducing it to its components and how they fit together. And we can keep asking that question, okay, what's a cell? How does it work? Why does a cell behave the way it does? And the answer is, at least one answer is, well, a cell is made of various protein molecules which fit together in a certain configuration. Great, so what's a protein molecule? Well, it's a bunch of atoms, hydrogen and carbon and nitrogen and oxygen and whatever it is that makes up a protein molecule, fitting together in a certain way, obeying certain rules. So we keep understanding complicated things in terms of simpler ones, which are more universal. By the time we get down to these atoms that make up the molecules, these atoms are constituents of everything in the world. So if you understand how they work in a protein, you also understand how they work in the frame of a car. So there is an appeal and a value to following this reductionist approach, even if it's not the only way. Particle physicists just ask, how far can we go? We've got these atoms. What are they? Well, now we have a mental model. They're made of a nucleus and electrons which orbit around it. It's a kind of a classical picture which we will be talking about in future lectures in this course. And then we can ask, okay, what's the nucleus made of? And we understand it in terms of smaller particles still, protons and neutrons, which themselves are made of something called quarks, a bizarre word which we're going to be learning lots about. So anything that's unfamiliar at the beginning of this course, hang on, we're going to be defining what's a quark and what's an electron and what's a lepton, and all the buzzwords of this field are going to make sense because it's really just a simple story. And in order to make sense of them, it's nice to have some mental framework, some model, and that model can be quite simplistic. It's perfectly legitimate to have a kind of a naive view to start with that gives you the essence of the story. I have to make an apology for reductionism because there's lots of discussion in the scientific communities about how useful and how important reductionism is. For example, supposing I want to teach you about music. I say, I want to understand Mozart. There are various approaches, and one approach might be to sit down at a piano, listen to the Mozart music, and figure out what the individual notes are that I'm hearing. I might write them down on a piece of paper with some lines using a scientific notation to encode which notes the music is made of, how long they last, and how loud or soft they are. Of course, that's the way musicians get the music. A pianist sits down and reads that notation and can play Mozart. So basically, as a reductionist, I've said Mozart is just 88 notes on a piano. I have reduced music to the simple fundamental building blocks, those 88 keys, and then the various properties they can have, how loud and soft, how long they last. That's a reductionist approach, and of course it's not completely satisfying. It's not just the names of the notes and the order. There's something deeper about Mozart's music that's compelling and beautiful, and so there's more to understanding the music than just knowing the notes, but clearly knowing the notes is useful and important and valuable. So this is where we're headed. We're going to be learning about the building blocks and how they fit together. But let me also, in this first lecture, before going into any of those details, which comes later in this course, ask the kind of big question, why is it that we care? I can't just give you a hard and fast answer to that question. It's perfectly legitimate. People will ask you, why are you taking this course? Why would you spend time and energy and money to try to understand particle physics? There are many reasons that I can think of. Many of them are personal reasons, and as the course goes on, I'm going to be asking this question at various levels over and over again. Why do we care about this stuff? It's interesting at many levels and in many ways. Let me throw out a couple of ideas to you today, and it's something that you should be thinking about, of course, for yourself as we go along. When people say to me, why do you study particle physics? If I'm sitting in an airplane and the person next to me learns that I'm a physicist, after their initial gut reaction, they want to know, what do we get out of this? What's the reason for studying particle physics? And I think that they're thinking about technology. That's what scientists are famous for. What has come out of this particle physics research that affects our everyday lives? And I can list some things. Particle physics is a bit of an esoteric field. We're really trying to look at microscopic objects, and many times these objects are so disconnected from the ordinary everyday world, it's a little bit hard to point your finger at some specific application. But there have been, in fact, many. There's a lot of medical technologies that make use directly of what we've learned about particle physics, from radiation therapies, proton beam therapies, to imaging of human brains with antimatter, PET scans. All of this stuff are really, in a direct sense, offshoots of the study of particle physics. If you allow me to generalize particle physics to modern physics, which includes the building ideas, quantum theory, and relativity, then all of a sudden I can point to just about all of technology. From television sets to microwave ovens to cell phones, all of that stuff relies upon and was developed from ideas of quantum theory. But if you're really focused on the particles and the particle physics, well, we've developed magnet technologies from the accelerators that were used to study the particles. But the particles themselves don't always enter into our life. And so it may be that I have to kind of back off and say, maybe this is not the reason why we study particle physics. Let me ask you this. Why did we go to the moon in the late 60s and the early 70s? When people ask NASA, what was the point of going to the moon? There's many different answers that they can give. And every now and again, you hear them say, well, gosh, the space program helped us develop Tang and Teflon. Right? Well, that's a nice idea, and I'm grateful when I'm camping that we have Tang, but it's really not the reason, to me, at all, for why we went to the moon. As you can imagine, there are much deeper, more profound reasons. Now, you can think about spin-offs in another sense. The space program teaches us about astronomy, it teaches us about materials, it teaches us about geology. In a similar way, particle physics can spin off. What we learn when we're studying particle physics is a mathematical description of how particles work together, interact, and form more complex structures. If you generalize that idea, you realize that you can apply it to something other than the fundamental building blocks. A biologist might take the same mathematical structures and apply them where your building blocks are now cells. And we can understand how an organism built out of cells functions in terms of a theory, which is really the same theory, a same mathematical framework as the particle physicists have developed. And this has happened over and over again. In history, all of science is tied together. There is no branch of science that's completely disconnected from particle physics, nor is particle physics completely disconnected from geology or astronomy or chemistry. It all ties together, so one can talk about applications in this scientific or intellectual sense. And sometimes it's even fairly applied. We have discovered particles of nature in particle physics, exotic particles with crazy names like muons and neutrinos, and we have begun using those, for example, as astronomical tools. We can use them to look at distant objects in a way that we never were able to before. We're going to be learning about that in this course. Those mysterious particles all do make sense. There is a simple picture that you can have in your mind of what a neutrino is and what a muon is, and then you will be able to understand at some fairly deep level what is that technology and why did it work. So this is spin-off still in some abstract sense, but I think we can motivate studying particle physics at a level that's really not even about applications. It's not about applying to technology or about applying to other fields. It's our innate human curiosity about the world. Right? We are puzzle solvers. I think it's genetic. If you go back 1,000,000 years and there's some cave people, I could imagine one cave person watches a rock tumbling down the cliff and saying, rocks follow parabolic arcs. The next time a rock is bouncing towards me, I know which way to step so it doesn't whack me in the head. And the one who wasn't curious gets whacked in the head and dies away. And one can imagine that curiosity is here for a reason. It's innate. We want to know, what's the world made of? At least I do. And since you're watching this course, probably you do too. What are those building blocks? Can we understand them? It's the same kind of appeal of a crossword puzzle or a jigsaw puzzle, except this one is real. It's not artificial. The world has provided us with this puzzle, and we want to know, how do we put it together? How do we solve these mysteries of nature? I think there's another level, which for me is some kind of, I don't know, personal satisfaction. So when I look at a rainbow, okay, it's a beautiful phenomenon. And some people would even say it's magical. And I understand the use of that word, and I feel that way. When I look at a rainbow, I feel that it's magical, and I love it. I will point it out to my friends, look, there's a rainbow, right? And we all enjoy it. But I think I get a deeper satisfaction from my understanding of a rainbow as a physical phenomenon. I know what's going on. There's little water droplets in the rain, and the sunshine is reflecting internally, and I understand enough optics to know why the colors appear in the directions that they appear at the angle it appears. And that doesn't take away any of the magic. It adds to me, to the pleasure and experience of this physical phenomena, because even though it is magical and mysterious, it also makes sense. The world is really fundamentally simple. At some level, everything from a rainbow to music to hard and soft objects, anything you can think of, all boils down to fundamental particles interacting with these fundamental laws. It's not about the facts themselves, it's about putting together those facts into a framework. Particle physics is in many ways regarded as the most fundamental. It's also, for that reason, the most abstract of any sciences. If you're a reductionist and you're trying to understand complex phenomena, they're interesting in their own right. A biologist trying to understand a human body is doing something very useful and very fascinating. The human body in all its complexity is great science. To me, it's a little overwhelming. I'm a simpleton. Physicists go for the simple underlying truths, and particle physicists really try to get to the very bottom as best we can. Now, I don't want to argue that we're done. I don't want to argue that today we know what the bottom level is. I began this lecture saying we do have a deep understanding of the world, and you will learn in this course about that deep understanding. It goes by the title, The Standard Model of Particle Physics. So this course is really about learning the standard model of particle physics. And I'm going to try to convince you that it is a deep, true statement in the scientific sense of the word truth. Not that it's the end of the line. Nobody knows. Maybe we will understand these deep truths in terms of yet deeper ones. That's certainly possible. And it's one of the open questions which we'll be heading towards at the end of this class, is how can we go beyond our present state of understanding? So our goals here are, without getting heavily into mathematics, in fact, without getting into mathematics at all, you can still create for yourself an understanding, a conceptual model, the standard model of particle physics, so that you can make sense when people are telling you in the news about some new discovery, when you are relearning something that you learned in your youth. It all fits together. The picture is really quite straightforward. In this course, we're going to begin with a sort of a historical format. I believe there's many ways to approach a broad field of human understanding. I think that it's nice to look back at the historical evolution of these ideas. Some of these ideas are pretty wild. Some of them are pretty abstract. Some of this stuff will feel a little bit like heavy going. And when that happens, we're going to just pause and look at the people who discovered it and the experiments that they did, which convinced them of these facts of nature. We're going to be looking at a progression of human thought which has reached a truly spectacular level. This is very accurate. This is quantitative physics, which allows you to make calculations and predictions, to design new apparatus. So we're going to be following this historical path, but not entirely. From time to time, there's a mystery that appears in the 1930s that we've solved today, and I'm certainly not going to leave you hanging. I want the story to begin to form a coherent whole right from the start. So we will be progressing along, fitting all the ideas into this standard model of particle physics. As I said, you do not have to be a physicist. In fact, I don't expect that anybody knows any particle physics, nuclear physics. You don't even really have to know what an atom is, except for some vague memories from your youth. Particle physics is a big field of knowledge. Okay, this first lecture has just tried to paint in very